Today we're going to talk about support vector machines, which are one of the two core topics on quiz 3, which is a week from Wednesday. So that's neural nets, which we talked about last week, and support vector machines. And then next week, Recitation, we're just going to go over some practice problems for both neural nets and support vector machines, so don't worry about it if you're still a little shaky on those. So support vector machines are a type of supervised machine learning, just like other things we've talked about, which were k-nearest neighbors, ID trees, and neural nets. So what all of these things do is they draw boundaries in some space. So for example, if we had this data, how would ID trees draw boundaries there? How many lines would you need with ID trees? One line? Well, let's say that you can only use X and Y tests. Or what one line would you draw? Yeah, we would need 2 lines if we're only using X and Y tests with ID trees. So we would have something like that and that, or there are other possible solutions. Nearest neighbors would just draw the perpendicular bisectors between plus and minus points. What would neural nets do? How many lines would a neural net need to draw?
1.
Yeah, just 1, because the data is linearly separable. So a neural net might do something like, say, that line. It might also draw one closer to the minuses or halfway in between, but the neural net is just going to separate the data somehow. A support vector machine, in this case, is going to be very similar to a neural net, but it's going to actually separate the data with the largest possible margin. So in this case, a support vector machine might be the best choice because it gives us this wide margin between the pluses and minuses, and it's not going to overfit. So an SVM, or support vector machine, is a numerical classifier. And what I mean by that is the data has these numerical features, which might be something like X and Y, so they're not symbolic features. And specifically, it's a classifier that will draw a single decision boundary such that it maximizes the margin width. So we could say it maximizes the margin between the plus and minus points. So one thing that I sort of glossed over is the support vector machine is a binary classifier that's classifying points as either plus or minus, whereas neural nets were classifying them as 1 or 0, but it was still binary. So it's basically the same thing. The classifications are just labeled differently. So now let's try this on another data set. Well, first let's say, what if we had exactly 1 plus and 1 minus point? There are a few different boundaries we could draw. So we could have something like this line A or this line B. Which one would be a better decision boundary? A, because it's maximizing this margin. So basically, the distance from A to any one training point is a lot bigger than the distance from B to a training point. So using that principle, what might we put as the decision boundary for this data? Yeah, x equals 1.5 would be good, because that's exactly halfway between the plus points and the minus points. So we could have this line, x equals 1.5. So we're going to say that's our decision boundary. And then because we're talking about the margin between the positive points and the negative points, we're going to put in these things called gutters. So the gutters are going to go through the closest negative points to the decision boundary and the closest positive points, and they'll be parallel to the decision boundary. So we'll have those two lines. One possibly confusing thing about the terminology is the gutter is not actually a region. The gutter is just the line itself. So you can't really be in a gutter, but you can have a point on a gutter. So these blue dashed lines are gutters. And then another thing we have are the points that determine the decision boundary, and those are called support vectors. So in this case, which points are necessary to determine the boundary? Yeah. Yeah, A, B, and D. And the reason why we know that is if we removed any one of those points, the boundary would be different. So what we have here are, we have 4 training points. We have 2 classes of points, plus and minus. And in this case, we have 3 support vectors, where a vector is just a point. And those are the circled pluses and minuses. So we could also add other extraneous points here. Like we could add other minus points out here or plus points out there. But they wouldn't change the boundary at all unless we put them inside this margin area. Oh, so the margin is another term. The margin is this distance between the 2 gutters, or this area between the 2 gutters. So this thing, that's the margin. And the margin width is the distance from one gutter to the other. What would be the value of the margin width in this case? 1, because it's just the distance from 1 to 2. So the margin width is equal to 1. Another thing we could do is we could add additional points, say, on the gutters. Would those be support vectors? So it depends on how we define support vectors. The definition is that they're any point that are necessary for determining the boundary. So if you could remove the point and the boundary wouldn't change, then it's not a support vector. So in this case, we don't need any of those points to be support vectors, but it's actually somewhat ambiguous because we could say that A, B, and D are support vectors, or we could say that D, B, and this point are the support vectors. So in this case, you can't tell exactly which points are the support vectors, but we only need 2 or 3 of them. So the different cases we could have in 2 dimensions, either we could have something like what we have right now, where we have 2 pluses and a minus, or 2 minuses and a plus, and one of the points is sort of between the others. And then we're going to have a total of 3 support vectors. Or we could have a case where we only need 2 support vectors, so if the points are directly across from each other. Like if we had a point right here, then we could use just D and that point. Another thing we can think about is what would happen in other numbers of dimensions. So in 2 dimensions, our boundary is a line. And we need either 2 or 3 support vectors. What about in 1 dimension? What would the boundary look like?
A point?
Yeah, a point. So in 1 dimension, the boundary itself is a point. So we might have, our data could look like this on a number line where we have some pluses and some minuses. And then that would be our boundary. What about in 3 dimensions? A plane. And so you could also do higher numbers of dimensions. They're just harder to draw on the board and think about. In 1 dimension, how many support vectors would we need? 1? Which point? What is a support vector?
2.
Yeah, 2. Because we're gonna need 1 plus and 1 minus. So you always need at least 2 support vectors. And in 3 dimensions, in some cases, we'll need more than 3, but we're not going to worry about that for today. So now one question could be, how do we figure out where this decision boundary goes? In this case, it was pretty easy to see that it was just going to be this vertical line, but sometimes it's not quite so easy. So we're going to have something called the convex hole method to help with that. A convex hole is basically a convex shape, so a shape that doesn't have any concavities. So what we're going to do is we'll start with some data. Maybe there's some pluses, and there's some minuses. And what we're going to do is we'll pretend that we're stretching a rubber band around the plus points and another rubber band around the minus points. So then that'll give us shapes that look like this. One thing that does is it makes it easy to see that some of the points definitely won't affect the boundary. Like this plus in the middle of the shape is definitely not going to be the plus that's closest to the minuses. Another thing is it makes it easier to see that this line is closest to that point. So in this case, we would have these 3 points being support vectors, and that would be our boundary. So this is one of 3 cases. This is the case where we have basically a line and a pointy area, where one area is plus and the other area is minus. You could also reverse them. And the boundary is going to be parallel to the line. And the gutters will just be along this line and then parallel going through that point. Another case we could have is if we have 2 pointy regions facing each other. So we might have something like there's some pluses and there's some minuses. So again, we can stretch rubber bands around them to make convex holes. Sometimes it's not entirely clear. So you might ask, well, is this point closest to that point, or is this point closest to that line? So the way we can figure that out is by imagining that we extend this line and figure out where is the closest point on this line to this point. And so that would be if you draw a perpendicular from this point to the line. And so then you would see that the closest point on the line is way out here. And so it's not part of the convex hole. So that means that this line does not determine the boundary. So in this case, all we care about is 1 plus and 1 minus. So our boundary will just be the perpendicular bisector of those. So this is our second case where we have a pointy plus region and a pointy minus region and a boundary that's the perpendicular bisector. And so then again, once we have the boundary, the gutters are pretty easy to find because they just go through those points. What do you think the third case is?
2 lines.
Yeah, 2 lines. So we might have something like there's some pluses, there's some minuses. So we put rubber bands around the 2 sets of points. And then we can see that these 2 lines happen to be parallel. So that means that our boundary will just be another parallel line there that's halfway in between the 2 lines. And then the gutters will go along those points. So this is the case where we have a plus region and a minus region that both have lines that are parallel. And then we have gutters. How many support vectors will we have in the line and point case? Yeah, we'll always have 3 because the point will always be 1. Well, I guess we could have only 2 if there was a point right there. So we'll have either 2 or 3. What about in the point and point case?
2.
Yeah, only 2 because we just have these 2 pointy areas. What about in this case?
Well, it could just still be 2.
So we said up here we'll only ever need either 2 or 3. So it's going to depend on if there are 2 points that are directly across from each other, we could say just those 2. Otherwise, we could say it's like these 2 and that plus, or 2 of the pluses and a minus. It's ambiguous, but we only need 2 or 3 of them. Are there any questions on that? Yeah?
So if they were to ask you what the support vectors were in that case, then are there more than one?
Yeah, there's more than one answer. So we could say, for example, that it's those 3 points, but you could also say it's the 2 minuses and this plus. Some answers would not be correct. Like if we said it's these 2 pluses and that minus, that wouldn't actually work because then the boundary would be diagonal like this. So you just have to make sure that the points that you choose do determine this particular boundary. Other questions? Okay, so this is sort of a human way of solving this problem because it's harder to tell a computer to stretch rubber bands around points and figure out whether they look parallel. So we're going to formalize this a little using some parameters w, b, and alpha. So w will be a normal vector, which specifically is perpendicular to our boundary. And b will be the offset, and it'll just be a number. So these are the parameters that the computer would use to figure out where the boundary is. But for now, we're going to compute w and b using our boundary. And then at the end, we'll talk about how the computer would actually get that boundary. So here's how to calculate w and b. So for calculating w and b, we're going to have 4 steps. And overall, we're going to end up with 5 equations. So I'll number them as we go just to keep track. But our first step will be, we'll just draw the boundary line. So this is still a human method, and we've done that. It's our pink line here. And then the next step is we'll figure out the equation. We'll write the equation of the boundary. What's the equation for our decision boundary in this case? Yeah, it's on here already, x equals 1.5. Okay, then our third step is we're going to rewrite this equation in a specific format. So we'll rewrite the equation in the form w dot it with x plus b equals 0. One note about this, in lecture we used minus b instead of plus b. It's not really going to make a difference because b is just a constant that we're figuring out, just that the sign of b would be different. But most notes use plus b, so we're going to do that just by convention. So what we're going to want is some vector w dotted with the vector x is just our features, which in this case are x and y. So if we were doing this in more or less dimensions, then this vector would have more or less things in it. And then plus some value b is equal to 0. So we're just going to reformat this equation similarly to how we did with neural nets. So we could say this equation is the same thing as 1x plus 0y minus 1.5 equals 0. So what would be the vector w? 1, 0, because it's 1 times x goes here, and then 0 times y goes there. And then what would be this offset b? Minus 1.5. So we can just read those numbers off the equation. But this equation has a degree of freedom in it, because we could multiply through this equation by something like -1 or 200, and it would still draw this exact same line. But what we want is we want a rule for classifying points, which is the classification of some unknown point x should be equal to the sign of the expression w dot x plus b. So that means that we care about whether or not we multiply through this thing by -1. So we need some way of scaling it. And we're also going to care about the degree of freedom so that we can use that to figure out how close we are to the margin. So what we'll do as our fourth step is we'll scale this equation. Specifically, we'll scale it so that the margin width is equal to 2 over the norm of w, which is an expression we derived in class. Oh, so the equation, this was equation 1 up here. And this thing with the margin width will be equation 2. But putting a constraint on the length of w still doesn't tell us whether or not we should multiply through by -1. So we're also going to say, and we want w to point toward the positive points, because w is going to be normal to this line, so it's going to go either to the left or to the right in this case. And so we want it to point toward the pluses. So that's one way we could scale this equation, but it turns out there's another method that's equivalent and actually easier mathematically. So equivalently, we can use something called the gutter constraint. The gutter constraint is going to be a constraint regarding the points on the gutter, as you would expect. And specifically, it says that for the support vectors, or for any other points on the gutter, we want this expression w dot x plus b to be equal to exactly plus or -1. So that means that this expression, when you're on the gutter, will be +1 or -1. When you're inside the gutter, it'll be between 1 and -1. And when you're outside, the absolute value will be greater than 1. And so that way, this expression will be able to tell us how far from the decision boundary something is. So the gutter constraint says w dotted with some point x sub I plus b should be equal to the classification y sub I for all the support vectors, or points on the gutter. And y sub I is the classification. So we can put where y sub I is the classification of the point I, which will be either +1 or -1. So what we're going to do in this case is we'll first use the gutter constraint to scale our equation, and then we'll check our work using the margin width and the direction of w. Oh, and the gutter constraint is equation 3. So in order to use the gutter constraint, we only need to choose one specific point that's on the gutter. So we could choose A or B or D, or we could even choose one of the non-support vectors. But let's just say we're going to use point D. So using point D, what we're going to do is we'll write out w dot x plus b for point D. So we'll have, we said w is 1, 0. X is the coordinates of point D. So what are the coordinates of point D? 2, 2. And then B we said is negative 1.5. And what do we want that to be equal to? What's the classification of point D? -1. So this is what the gutter constraint says should be true. Is it true? What's the left side equal to? .5? Yeah, positive 0.5. So that means this equation currently doesn't hold, but that's why we need to scale it. So the thing we're scaling is we're scaling W and we're scaling B. So we could write that as some constant times W plus some constant times B. Equivalently, we could just put a C in front of the whole thing and scale the whole W dot x plus B thing, and it would be the same. So we could say this is the same as C times 0.5 is equal to -1. And then we can use that to solve for the constant C. So we get C is equal to -2. So that means that the gutter constraint tells us we should scale this equation by a factor of -2. So that will give us our scaled W is instead of 1, 0, we'll have -2, 0. And the scaled value of B instead of -1.5 will be +3. So that means now if we want to classify points, we can just use this value of W and that value of B, and it'll give us the correct sign. And it'll give us, yeah?
How did you choose -1 versus +1 over there again?
Yeah, so this is the classification y sub I. So if we had used A or B, then we would have done +1. But because it's a negative point, it was -1. Yeah, good question. So now we could use this to classify points, and we would find that the expression W dot x plus B will be between -1 and 1 if you're in the gutter, and absolute value greater than 1 if you're outside of the gutters. So the next thing that we'll want to do is calculate these supportiveness values. Well, I guess we haven't said what supportiveness is yet. So they're alpha values. Oh, actually, first we should check our work here. So let's see what happens with the margin width. So if we use equation 2, which says that the margin width should be equal to 2 over W, this should now hold now that we've calculated, now that we've scaled W. So let's see if it's true, margin width. So what is the actual margin width in our problem? It's on the graph. So what did we determine was the margin width just by inspection? 1, because we said the margin is this distance between the gutters, and that was equal to 1. So this should be 1. What's the length of the vector W? 2. So 1 is equal to 2 over 2, and that's correct, so that's good. And then we just need to check that W points toward the positive points. So if W is the vector -2, 0, if we drew it from the origin, it would go like that. Or if we drew it from our boundary line, it would go like that. So it does point toward the positive side, so that checks out too. So that means that these values of W and B are consistent. Yeah.
Is W defined as like the line normal to the boundary?
Yes, so W will always be a normal vector to the boundary. One slightly confusing thing is that it's inversely proportional to the margin width, so as the margin gets smaller, W gets bigger. So it's a little dangerous to think about it in terms of representing the margin width. You just have to remember that it's opposite. Any other questions on this? Okay, so now let's go on to calculating the alpha values. So these are the parameters that determine how we classify things, our classification rule. But the way that the computer does this, instead of finding the boundary by some magic, it has these alpha values which are Lagrange multipliers. And if you don't know what that means, don't worry about it. But basically, they're values where each point has one. And the computer is going to use something called sequential minimal optimization, where it goes through a bunch of iterations where it adjusts the alpha values until it maximizes this margin width. So we're going to calculate what the alpha values will be at the end of the problem after the SVM has been trained. Another name for these, we're going to call them supportiveness values. Because another way of thinking about these alpha values is they represent how big of a role each point plays in supporting or determining the boundary. So that means that a point like E out here that doesn't play any role in determining the boundary will have a supportiveness of 0 because it doesn't determine the boundary. So our first step here will be to find all of the points that aren't support vectors and just give them alpha equals 0. So for all non-support vectors, alpha is equal to 0. Otherwise, the point is a support vector and it lies on the gutter. And it's going to have a positive supportiveness, so alpha greater than 0. So note that the supportiveness values will never be negative because no point is going to contribute negatively to determining the boundary. So then we'll have two more equations to figure out what these values actually are. These are equations that we derived in lecture. The first one will be the sum over all of the support vectors. So each support vector I of their supportiveness values times their classifications will be equal to 0. But because there are only two possible classifications, either plus or minus, we could write this equivalently as the sum over the positive support vectors, which we'll call P, of their alpha values is equal to the sum over the negative support vectors of their alpha values. So let's see what this equation is for our support vector machine. So we have three points that we're considering, A, B, and D. So we'll start with, we have alpha A times, what's the classification of point A?
Positive.
Positive, so times plus 1. And then B is also positive, so plus alpha B. And D is negative, so we'll have minus alpha D equals 0. And so I can say equivalently, it's the sum of the positive points alpha values, so alpha A plus alpha B is equal to alpha D. And you can see that those are equivalent because we just moved D to the other side of the equation. So this will be equation 4. And now we just need one more equation so that we can solve, well, we need another pair of equations so that we can solve for these three unknowns. So we're going to get that by doing another summation over the support vectors. And this time we're going to sum their supportiveness values times their classifications times their coordinates, and that's going to come out equal to W. So this is a vector equation, and we could equivalently write that as the vector W is equal to the sum over the positive support vectors P of their supportiveness values times their coordinates minus that sum over the negative ones. So our positive support vectors, we have A and B. So on this side of the equation, we'll have alpha A times, what are A's coordinates? 1, 3. Plus alpha B times, what are B's coordinates? 1, 1. And then minus alpha D times, what are D's coordinates? 2, 2. And that's going to be equal to the vector W. What did we say W is? Do we know what W is? Yeah, negative 2, 0. We computed that earlier. So we should make sure we're using the scaled w, because otherwise it's just some arbitrary vector that's some scaled version of that, where we want the actual w. So now we have 3 equations, because we could expand this out into two equations where we have negative 2 equals 1 alpha a plus 1 alpha b minus 2 alpha d. And then we also have the second line. So now we have 3 equations and 3 unknowns. So you can take a minute and solve for alpha a, alpha b, and alpha d. And we'll see if we get the same answers. Did anyone get an answer yet? Yeah.
Alpha a is 1, negative 1, and then alpha b and alpha g are 1.
Did you say 1 or negative 1?
Negative 1 and 1, 1.
Okay, so if we get a negative 1, something's wrong, because they should all end up being positive. So that means we made a mistake somewhere. What were the other values you got?
It relied on the negative 1, so.
Okay, I think they were correct, though, the other ones.
1 and 1.
For alpha b and alpha d. So we have alpha b is 1. What you said, what was d?
I said 1.
Okay, it should be 2.
Alpha equals 1.
Yeah, so alpha a equals 1 based on this equation. Did anyone actually get these answers? Did we make a mistake somewhere? Are these answers correct? Yeah? Okay, great. So a couple of ways we could check these if we're not sure. The easiest thing is just plug them into the equations and see if the equations hold. Another thing to get more intuition is the sum of the alphas on the plus side is equal to the sum of the alphas on the negative side. So if we write them up here, first, what's the alpha value for E? 0, because it's not a support vector. And then we have alphas 1 for A, 1 for B, and 2 for D. So sure enough, the alphas on the plus side add up to the ones on the minus side. And that's true just because of this equation. Another thing to notice is the sum is that alpha A and alpha B are the same because those 2 points are symmetric with respect to point D. So in terms of how much of a role they play in determining the boundary, they're each working just as hard, so there's no reason why one should have a different supportiveness value than the other. Another thing to notice is that D has a greater supportiveness because it's the only point determining the negative gutter, whereas we have both points on the positive gutter. A couple other things we can look at for intuition are what would happen if we made the margin a lot wider. So let's say that we had the same sort of situation, but we now have A way out here and B way out here, and then D way out here. How do you think that would affect the supportiveness values? Well, we can find out. Yeah, they would increase? Okay, let's see if that's correct. So one thing that we notice is that the margin width is now a lot bigger. So the margin width increased. And that means that the expression 2 over w, which is equal to the margin width, also increased. So that means that w is going to decrease And equation 5 over here basically tells us that the supportiveness values are proportional to the vector w. So that means the alphas are going to decrease. And the intuition behind that is, over here we had this really squished together margin, so there wasn't very much wiggle room. If we moved a point even a little bit, it would change the boundary a lot in comparison. Whereas here, because the margin is much wider, if we move one of the points, it won't change the boundary significantly. So we're going to say that here the points are playing a lesser role in supporting the boundary than here when there's a really small margin. So an example of the alpha values here might be, say, 0.1, 0.1, and 0.2. So they'll still be in the same ratio as in this case. Are there any questions on why that is? Okay, and then one other thing we can look at for intuition is, let's go back to having our small margin. But let's say that we have A up here, B down there, and D a lot lower, close to B. So we could say that D still has a supportiveness of 2, because the margin width is the same as in this case. But now the question is, which one will have a bigger supportiveness, A or B? Here, I guess for B. So a way to figure this out is to see what would happen if we removed either of them. So if we moved point A, then the boundary would change a little bit and it would look like that instead. Whereas if we kept point A but removed point B, the boundary would swing around and look like that. So that means that B is playing a greater role in determining this boundary. So as you guessed, it's going to have a larger supportiveness value. So we might have something like alpha is 1.8 for B and 0.2 for A. The exact numbers are going to depend on how far apart they are with respect to D. But those are just an example of what we might get in that case. So any questions on calculating W, B, and supportiveness values before we move on to kernels? Okay. So far we've been assuming that our data is linearly separable. But oftentimes that's not going to be the case. So we'll need some other way of handling it. So if the data is not linearly separable, we have a couple options. One thing we can do is apply a transformation, such as transforming to polar coordinates. Another option is, instead of using a dot product, to replace it with something called a kernel function. So we'll replace the dot product wherever it appears, like in w.x plus b, with some other function. This other function is called a kernel. And this basically has the same effect as transforming the space, except that we don't have to actually apply a transformation. So one way of thinking about this kernel function is it's a similarity measure. And we're going to do a very short derivation to see why. So a kernel function such as some function k that takes in two vectors u and v is a similarity measure. And the reason why comes from this equation for classifying points. So the classification of an unknown point we said was equal to the expression w, or the sign of the expression, w dot x plus b. But we could replace w using equation 5 with this expression, and it would be the same. So we're going to do that. And then we get this is equal to the sign. We replace w with the sum over all of the support vectors of their supportiveness values times their classifications times their coordinates, dot that with x, and then plus b. So one more thing we can do is we can take out this dot product x sub I dot x and replace that with a kernel function. And so then we have the sum of the supportiveness values times the classifications, but then we have a kernel function in our sum, which is the kernel function of x sub I and x plus b. And so when we have the kernel function is equal to x sub I dotted with x, then that's the exact same thing as the expression above. But the neat thing to notice here is when we're classifying unknown points, so if we have some mystery point over here that we're trying to classify as a plus or a minus, the alpha values aren't changing. The classifications of the support vectors aren't changing. And the value b isn't changing. So the only thing that changes is this kernel function. So what I mean when I say that the kernel function is a similarity measure is that basically the way that we're figuring out the classification of this unknown point is we're using the kernel function to see how similar it is to each of the 3 support vectors. And we're using that to determine is it more similar to the pluses or more similar to the minuses. And that tells us whether it's a plus point or a minus point. So we're going to look at a few common kernel functions. So far we've just been using the dot product, which is a linear kernel, and it draws a single line in the space. So we could also have other linear kernels that would similarly draw a line. We'll make a list of common kernel functions. So a linear function, for example, the kernel of 2 vectors u and v could be their dot product or their dot product plus a constant, and that will still just draw a line. And then we could do something more complicated like a quadratic kernel. For example, the kernel function of u and v could be equal to u dot v plus 1 all squared, or basically any quadratic function of the vectors u and v. So if a linear function draws a line, what do you think a quadratic function does? Yeah, something like a parabola. So it basically draws any conic section. So this could draw a line. It could also draw a hyperbola. So if our data, for example, looked like this, then it might draw a parabola. It might draw a parabola. It could also draw a circle or an ellipse. So it could do something like that to classify this data. Or it could even draw a pair of hyperbolas. That's a tongue twister, which is another conic section. So this might look like 2 lines, but it's really only one boundary because it's a single function that draws both of those. And then we could also do a higher order polynomial, which is just the same idea but a more complicated polynomial. So we could give it some more complicated data, and it might do something like that, for example, which is a cubic function. And finally, the last kernel is something called radial basis kernel. The main things to know about this kernel are that it's really powerful and can classify basically any data set, unless you have something like a plus and minus point with the exact same features, in which case nothing will be able to classify it. And so basically that it can classify any data set. And the way it does that is sort of, you can think of it as drawing fuzzy nearest neighbor type boundaries around all the points. So if we have, well, so first an example of a radial basis function. The general form is the kernel function of two vectors u and v is equal to e to the difference between them over some parameter sigma. So this parameter sigma is a Gaussian parameter. And depending on how we tune this parameter, this might draw different things. So like if it's tuned to prefer minus points, it might do something like drawing little circles around the pluses so that almost everything is classified as a minus. Whereas if it's tuned to prefer to treat them equally, then it might do something more like that. And so again, this might look like it's drawing multiple boundaries, but the way to think of this is it's really just drawing something in another plane. So if we turn this on its side, then what's actually going on is there's a function that's coming out of the board, and it sort of has two little mountains coming out of the board that look like that. So these are the things coming out of the board, and where they intersect this plane, they form circles. So it's not actually two separate circles. It's really just a manifold or a floppy plane that's sort of coming through the board in various places. So basically with that, you can classify anything because you're adding another dimension to your classifier. Any questions on that? So that's basically everything that you need to know about support vector machines.